Hello everyone, and welcome to my presentation of efficient homomorphic evaluation of KNN classifiers. It's a work that I've done with Renaud Sirdey for CEA List. I'm going to have a very small introduction, hopefully, and then I'm going to present our contribution. And first, our contribution explained in the context of cat privacy. If you have a user who has a picture of their cats and wants to know which one of them is the cutest, maybe that user doesn't know how to answer that question, but a server has a very complex cuteness determination algorithm that can do just that. So how can both of them help each other? Well, one way to do this is for the user to send the clear text picture of their cats to the server for the answer to come back from the server after computation. But this means that the privacy of the cats is compromised here. And another way to do this is for the server to send their complex algorithm to the user for a computation on the user side, but that means that a very complex and maybe very expensive algorithm is just sent out in the open. So that's a bit of a problem, and one solution in the state of the art is fully homomorphic encryption, and its promise is that given a function f that is applied on a certain number of inputs, we can just encrypt those inputs with a fully homomorphic encryption scheme and just apply very easily that same function f and obtain an encryption of the result. Now, what would that mean for our cats? Well, in that case, the user can just encrypt the picture of their cats and send it over to the server, who can then compute over encrypted data and send the result back. That way, both the complex algorithm and the privacy of the cats is protected. The encryption scheme that we've used for this contribution is TFHE, Torus-based, LWE-based encryption scheme. And on top of knowing that, well, it's based on Torus, which is the additive group 01, one thing that's important is that, as with every other LWE-based encryption scheme, there is an error that is introduced during the encryption. That means that at decryption time, the message that is retrieved has to be matched to the closest message in the message space. Now, the operations that we have are internal addition, a ciphertext with a ciphertext, and an external multiplication of an integer clear text with a ciphertext. Now, both of these give us a scalar product between an integer clear text vector and a ciphertext vector, which is actually a squared Euclidean distance. And another operation that's a bit more complex and that's quite specific to TFHE is going to be the bootstrapping operation that does three things. It outputs a fixed noise, it switches the encryption key, and evaluates a function, which in our case is going to be the sign function. Now, this is going to be a very interesting operation because of a problem that most homomorphic encryption schemes have, which is error management. As we said, there is an error which is introduced at encryption time, and this error is going to grow with every operation that we apply on our ciphertexts. And at some point, decryption is going to be impossible. So there's two solutions to this. One is to use a leveled homomorphic encryption, and that means setting the parameters so as to stop the computations exactly when the error has not yet grown too big. And that means knowing the depth of the computation before we set the parameters, and that can be a problem in certain use cases, and that's the reason why we can use fully homomorphic encryption to solve the same problem, and that requires resetting the noise of the ciphertexts mid-computation. That's the point of the bootstrapping operation in our case. If we take a real value m on the real axis here, before it can be encrypted using TFHE, it needs to be encoded into a torus value by dividing it by a base b, and therefore it's going to get into this circle, which is the torus, with the lower values here being from -1/2 to 0, and then from 0 to 1/2. The positive values on top, the negative values on the bottom. Then encryption adds an error, which is represented by this squared area here. And the bootstrapping operation is represented by this circle with red zones around 0 and 1/2, which is where the bootstrapping operation is going to output errors. So the bootstrapping outputs a value which is then decrypted, removing the error, and then decoded by multiplying it by the output base, which in this case is 4. So here we get an output of 1 at the end for an input which was positive, so that's a good application of the sign function. Equivalently, if the initial input is negative, then we're going to get an output of 0 at the end. And if the encoding of the initial input is too close to the value 0 in the torus, then the bootstrapping operation can get a wrong result, in this case 0 for a value that was negative. Onto our contribution, and first a word on k-nearest neighbor classifiers. They're very simple kinds of machine learning algorithms that are still very much used today in real-world applications, especially since the advent of embedding-based neural networks. And for a very simple example here, if you want to classify an unknown voter as having an affiliation to either Democrats or Republicans for an American election, then we just place all known voters in a Euclidean space and place our unknown voters in that space. And then we either affiliate it to its closest neighbor, here a Democrat, or just have a majority vote among its 3 nearest neighbors to affiliate it here as a Republican. And the number of closest neighbors that we choose is the number k of k and n. So, in simple terms, what we have is one clear vector, which is the new vector to be classified, and a bunch of encrypted model vectors, which corresponded in our case to the voters that were already affiliated. And what we want is an encrypted vector with a whole lot of zeros and just k ones at k indices, which are the indices of the k nearest neighbors. First, let me present a leveled homomorphic one nearest neighbor computation. And on the left here, every operation done in a clear domain. And we start with some distance computations. And then we're going to, for every distance k and dk and dl, we're going to compare those two and compute a delta kl, which is going to only be equal to 1 if the distance k is lower than the distance l. And this is going to give us a matrix of deltas, and we're going to sum all of the columns of this matrix in order to get big deltas. And what we need to understand here is, for instance, if we take this first column here of deltas, if all of the deltas are equal to 1, that means that the distance 1 was smaller than every other distance. And this is only going to be the case for the smallest distance. So we're going to have only one column which is going to be full of 1s, and every other column which is going to have at least 1 0 among the deltas. So that means that in order to determine the smallest distance, we can just ask of these big deltas here, which one of them is equal to d minus 1, which would mean that all of the deltas in their column are equal to 1. And this algorithm here is going to give us the one nearest neighbor vector as an output. And in the encrypted domain, how we can do this is, well, just compute the distances, or rather the squared distances. I should have changed this to start with, as we saw with our scalar product. And this gives us a ciphertext with an underlying message which can be anywhere in the torus. Then we apply a sign bootstrapping operation in order to get our delta matrix. And we're going to extract here the first column as an example. We have a number of delta values here which can either be equal to 0 or 1, which is actually 1 over something encoded in the torus. Then we're going to sum all of these values together and get a value which can be anywhere between 0 and d minus 1. And we want to select the ciphertext, which includes the value which is equal to d minus 1. And for this, we're going to apply a little bit of a rotation and then a bootstrapping operation, which is going to make it so that only the d minus 1 value is going to be in the lower half of the torus here. So that means that the output of the bootstrapping operation is going to be equal to 1 here only for one of our big delta ciphertexts. And so with this, we have a leveled homomorphic one nearest neighbor computation. Now, this is a labeled scheme because if we add a number of model vectors here at the beginning, then we're going to increase the number of delta ciphertexts that we sum before a bootstrapping operation. And if we increase this number too much, then the error of the sum is going to be too big for the result of the bootstrapping operation to be correct. And in order to change this leveled homomorphic scheme into a fully homomorphic computation, we're going to have a very simple fix here. If we take the sum of the delta ciphertext here, what we just need to do is to separate these delta ciphertexts into fixed sized groups and then just apply the same computations, so a sum and a rotation and a bootstrapping operation in order to create some sort of intermediate deltas that we can just then keep summing and applying these rotations and bootstrapping operations. And so if we do this with fixed sized groups every time, we're going to get the same result in a fully homomorphic manner. And now to build a KNN from this 1NN classifier, if we take our leveled homomorphic 1NN classifier here, we're going to see that actually counting the number of zeros in every column is going to be very interesting and give us more information than just which distance is the closest. Indeed, if a column has only 1 0 on top of the diagonal here, of course, then that means that that distance is going to be the second smallest distance, etc., etc. So in order to determine the k smallest distances, we can just replace this question here by the question, is our big delta greater or equal than d minus k? And this is going to give us an output with k ones exactly at the right indices. And what this means for the ciphertext space is just a bigger rotation, meaning that we select here the k smallest distances, which means the k biggest deltas at the end. And this is a pretty nice change which gives us a leveled homomorphic KNN classifier. Now transforming this leveled computation into a fully homomorphic computation means introducing a scoring operation, which we're going to apply on a subset of deltas from a column. And what this scoring operation will do on this subset is it's going to start with a score of k, and then every time it finds a 0, it's going to reduce the score by 1. And this is going to be interesting for us because, of course, if there is more than k zeros in a single column, that means that the distance in question is not among the k smallest distances. And how we're going to compute this scoring operation in the encrypted domain is just sum all of our deltas and then apply a different set of rotations in order to select 1, then 2, then 3, etc., with the maximum being k maximum values every time, and then sum the results into something which is going to be between k and 0 and is going to be the score of our subset of deltas. And then, just as before, we're going to iterate this scoring operation on fixed sized groups in order to make our computation fully homomorphic. And this will actually give us the correct result, which is going to be either a 0 or a 1 for every column. 0 if it's not among the k smallest distances, and 1 if it is. What's actually really interesting about our implementation is that these k bootstrapping operations here are not actually k bootstrapping operations, but just k extractions at the end of a single bootstrapping operation. So if you have like the original bootstrapping, signed bootstrapping algorithm here on the left, then the only change that we have for our scoring operation is just k extractions here at the end instead of one, which is really interesting. Our results can be summarized with a very high accuracy as tested on the well-known MNIST dataset and the breast cancer Wisconsin dataset, and a bad scaling time-wise because of its quadratic complexity in nature. Now, in order to reduce the time complexity of our scheme, what one could want to implement it using a sort of more traditional tree-based approach, and that would mean having the distances here encrypted at the start and compared using the sign function, and then one of them being selected using a mux gate, and then going on and on, descending a tree like this. And this way we would have a linear complexity. And it would be very interesting, except that we have a few problems with these. One of them is that this mux gate here, when implemented homomorphically, has a huge error growth in it. And that means that we are not going to be able to go very far using this sort of tree version because of the error propagation that we have, and we're going to have very big parameters, and also because the error is going to grow every time, we might want to use some sort of identity bootstrapping operation, but then we're going to reduce the precision with which our distances are encrypted. Now, to give an example, for instance, with the 64-bit version of TFHE, we have a precision of 64-bit, and using an identity bootstrapping operation, we would go down to about 8 bits of precision, which would affect the overall precision of the KNN classification. In conclusion, we have a highly precise, fully homomorphic KNN implementation, which has a very good scaling in terms of precision and parameters because of its fully homomorphic nature, and bad scaling in terms of time. Now, I think there's a lot of perspective in order to improve maybe this scheme depending on the constraints in the use case, and mixing some sort of leveled scheme with our fully homomorphic scheme in order to boost the time performance but keep the precision of our scheme. And what's important here is that this very basic machine learning algorithm has really a host of applications in state-of-the-art modern machine learning. Thank you very much. This is my presentation, and I'll take questions now if you have them.